which we'll be using for the rest of the workshop.
Okay, so well, essentially we've already completed this workshop. You've already made a plugin with Gggc. It's just not a particularly interesting one, and we haven't really showed off anything that any of the capabilities that Gggc provides you. So from here on in, we're going to keep adding things to this plugin and showcasing some of the things you can do. This one will be the easiest. We're just going to go in and add a very simple gain reduction to the plugin. So show you how you can actually modify audio that's running through. If you are still struggling, then it might help if you copied the contents of the O2 directory into Workspace and then open the IDE project file directly from there rather than messing around with the producer. But if you have managed to keep up with this and you've got been able to load the plugin in the test host, then don't worry about it. So if you open up the project in your IDE, this is showing it in Xcode, we're going to work inside the plugin processor CPP file. Which is here. And the first thing you'll notice is that there's quite a lot going on in here. Almost all of this is filled out by the default plugin template in the producer, and it's setting things like, does your plugin handle MIDI? Is it a MIDI effect? What's the name? And various other kind of more general plugin configurations. But we don't need to worry about any of that. The actual audio processing is done in this function called process block. There's the implementation. Hopefully, most of it is fairly self-explanatory, but this is just like a skeleton for getting you looping over the audio, the incoming audio, and down here we're getting a right pointer into it, which is where we can make some changes. So process block is called repeatedly by the host with a chunk of audio to process. Your host typically have a setting that corresponds to the buffer size, usually a small power of 2, like 1024, 512, and this tells the plugin, or at least the host sends that number of samples in each buffer to the plugin. Something we will touch on again, but is useful for noting here, is that process block will be called on the audio thread, and the audio thread is not the same as that used for rendering graphics to your screen, handling mouse events, most file, I/O, and other things like that. And you should try as hard as you can not to mix the two. You'll notice that the first parameter in the process block function is this thing called a juice audio buffer. And it's this that holds the incoming audio data. Specifically, it's a class containing non-interleaved channels of audio data, where non-interleaved means that we have separate channels of contiguous audio data. So if you say, get me the data for channel 1, this will then be a series of floats where the value of the float ranges between -1 and 1. This gives you the amplitude of the audio. If you plotted it, this would literally be the waveform of the audio coming in. We're passed a reference to an audio buffer, which means that we can modify it, and any modifications to the audio is then passed on into the rest of the signal processing chain. If we change samples in this audio buffer, that's how we're going to affect the audio passing through this. That's exactly what we're going to do. We're going to zoom in at the bottom of this process block where we're getting a right pointer into our buffer, and we're going to modify it. I'm going to modify it in a very simple way. But I'm also going to copy and paste a because I've found that typing in front of an audience, even a virtual audience, makes me almost incoherent. So what have we done here? So we can see coming into this function that we're found out the total number of input channels, and we're looping over them. And we're saying for every channel of audio that we have, we're going to get a write pointer into the samples in that channel. And then we're next going to find out how many samples of audio we have. And for every sample in the channel, we're going to multiply its value by 0.2, or equivalently divide it by 5, where the net effect of this is going to be that the amplitude of all our samples is reduced to a fifth of what it was, and then that will reduce the volume. So let's see it in action. We're going to go up here and make sure we're going to build a plugin rather than a standalone. I'm going to build it. I just hit Command B, but if you go up to the top, you can go Product, Build, and it's a very similar workflow on Windows. And our project is built. So we'll open up our test host. Our plugins is in the plugins directory. We'll drag this over to our test host. There's our plugin, still the same default GUI, but now anything running through it is much quieter than when we bypass it and we're not processing the audio. So we see we're having an effect on the audio that passes through. This is kind of the building, but the most important thing that plugins do is we modify the audio in the process block function. So that's how we modify audio, but you've noticed that it's not a particularly dynamic process. When we compiled it, we had a hard-coded value of 0.2, which can't be changed at runtime. So this is very fixed. The typical way of dealing with this in plugins is to add parameters, and plugin parameters are actually part of the plugin's interface. So when a host loads a parameter, it will query the parameter for various things. One of the first things of those is how many plugins do you have, what type are they, what are their names, and things like that. And because this is published as part of the plugin, this allows doors to do things like present generic UIs where everything is a slider. It enables you to do things like record automation. And you as a plugin author, it lets you kind of better encapsulate the logic of how you can interact with whatever audio processing algorithm you have sort of further down the chain. The other thing to mention is that parameters don't have to be visible to the host. If you mark a parameter as non-automatable, then you, as a plugin developer, can see it and can use it, but it won't be exposed to the host for automation and other things. The easiest way of doing this within Gggc is to use one of the audio processor parameter subclasses that we provide. These are a nice wrapper around parameters where the audio processor parameter classes provide methods for getting and setting parameter values and properties. And when you add these to your audio processor takes care of their lifetimes and interacting with them. And we've got a handful of basic types to get you started, where a float parameter is something that is very suitable for something like a slider. A bool would be a button. A choice would probably be a drop-down, and an int would be some kind of discrete setting. And we will add a parameter in the constructor. So again, this is in our audio processor CPP file. If you go up to the top. We're going to add a parameter. And we do this by calling a method on our audio processor, which is add parameter, and passing that one of these pre-built parameter subclasses that I mentioned on the previous slide, where the parameters of the constructor of the parameter object are, this first one is an internal ID. So later on we'll show you how to refer to our parameters by these internal IDs. The next one is a public string to represent the parameter. So this would be displayed in a door, for example. And we have a minimum value, a maximum value, and a default value. And then once we've added our parameter to our audio processor, that then becomes part of the audio processor interface. So now we have our parameter, we need to be able to sort of get its value and feed our parameter's value into the audio processing that we're doing. And the steps we're going to take is this. There is another member function on our audio processor class, which is get parameters, which returns us a list of the parameters that we've registered. In this case, we've only told our audio processor about our gain parameter, so we only have one element. Take that, and that is our gain parameter. From there, we can ask it what its value is, store that, and then when we loop over the data in our audio buffer that we're modifying, we can, instead of multiplying by a fixed value of 0.2, we can now multiply the gain by, or multiply the existing samples by the value of the parameter. Again, I will copy and paste that in and go through it again, just so anyone who is typing and keeping up has a chance. We went down into our process block. So previously, if we ignore these two lines, and just down here, we are multiplying by a fixed value of 0.2. Now, instead, we're going to multiply this float value called gain, where this floating point value we've obtained from our gain parameter by asking it what its value is. We've got the gain parameter by asking the audio processor to give us all of the parameters that it knows about, where we take the first element, because we know we've only got a single gain parameter. Now if we build this, again I hit a shortcut, but you can go to product, build, or the equivalent in your ID. We fire up our test host. We can drag a plugin over. And I've missed an important step. The other thing we're going to do is stick up an automatically generated user interface. So you notice there, I came to go and modify the value of the gain and was greeted with just with the default hello world GUI, which I couldn't really do much. One of the bits of machinery that Gggc provides is a thing called a generic audio processor editor. And when you create one of these, rather than the default, this one is a bit smarter. So it will look at the audio processor that you pass to it. It will work out what all the parameters you've registered are, and then if it's a float parameter, it will display a slider. If it's a Boolean parameter, it will display a button, and so forth. So it's just a very quick way of throwing together some usable GUI. So that is just below our process block. There's this function called createEditor, and instead of returning the editor that's defined in our plugin editor source files. We're going to return a new generic audio processor editor. Then, build this. Fire up a test host. Load the plugin that we've just built. Then, see our gain parameter. So now, with a gain of 1, get a full volume, turn the gain down. It's much quieter. So we're going to start adding a bit of complexity, and for this section and the following one, it's best to sort of review the code changes as we go through. First off, because like adding a delay effect has a reasonable amount of code just to implement the delay algorithm, and this is a workshop on how to make a Gggc plugin, not how to implement a delay effect. And in the following section, it's because the code isn't particularly interesting to type in yourself. Like here, it's quite easy to see where you could change something like a single number and see that reflected in the GUI or how your plugin sounds. But there really isn't that opportunity in these sections coming up. I can see a question that is, how do I load the built plugin into the test host? Well, I'll just show you doing that again. So you go down here into the test host, you find the test host for your platform, fire it up, and if you have built your plugin correctly, then you will see this plugin appear in the plugins directory of the materials. And then you can simply drag that and drop it here. Click it, you can load it up and see it. Right. So yes, with the caveats that if you're going to keep up now, you're going to have to be a really speedy typer. Let's go ahead and look at the code that we're going to add, rather than trying to keep along. So we should briefly tell you what a delay effect is, so you can just have a bit of understanding of what you're going to hear. Delays typically introduce echoes of incoming audio. So when we send some audio to this plugin, it's going to remember it, and we're going to combine we're going to take any new audio and combine it with previous audio where we've heard at the time D, in this case, that has been recursively attenuated. Every time a time D comes, you would hear an echo from time D, but with time it's going to get quieter and quieter. A very simple delay is going to feature a fixed delay time, but we're going to add two new parameters. One that will determine how quickly these echoes will die away, and another one which is a dry-wet mix control, where a completely dry sound is only the input and a completely wet sound is only the echoes, and this will be a fade between those two situations. So the first step is to add those parameters, and this should be fairly unsurprising. We have this first line, which is the same as we had before, where we added our gain parameter, and we just add two more lines, this time with a feedback parameter, where the only difference is that it has a default, the extra parameters that we're adding happen to have the same values. We're going to change them both between 0 and 1, but they have different default values. So the default for the feedback starts on 0.35, and the default for the dry wet mix length is going to be 0.5, which is an equal blend between the dry and the wet. To do the delay algorithm, we're going to have a bit of state. We're going to have to remember a bit in our audio processor. And this is a simple circular buffer of audio history, where the size of the circular buffer, so a circular buffer is you keep writing audio data into it. When you get to the end of the buffer, you go back to the start of the buffer and just overwrite whatever is there. So that's going to be our kind of echo length. And each time we go around, the audio data that's already in there is going to get quieter. So the size of the circular buffer is going to determine the fixed delay. And each call we get into process block, we're going to add that audio into the circular buffer. So here's our bit of state. We go this time into the header file rather than the CPP file, and we add a couple of member variables to our class. This is the delay buffer that's going to hold our samples. We need to keep track of the position within the delay buffer that where we're currently at. And this is something new. So before, when you're using Gggc, before any calls to process block, before you do any audio processing, you will always get a call to prepare to play. And this gives you the chance to configure your algorithm for the subsequent calls to process block. In this case, we're going to need the sample rate. It would also give you an indication of how many samples per block you're likely to get. But we don't need this for now. So I said a few slides before that our delay is going to feature a fixed delay length. In this case, it's 200 milliseconds. Now, if or at least if your plugin is dealing with audio that has a higher sample rate, then you have many more samples in 200 milliseconds. So we need to size our delay buffer appropriately. So with increasing sample rate, you can see that the size of our buffer also increases. And then once that's done, we can call, we don't call, the host will call process block, and we will be configured correctly. And this is the delay algorithm, and we'll zoom through it. So the first thing we do is we get our parameters, like we've done previously, where we now, rather than just a gain parameter, we also have a feedback and mix parameter. And if this seems fairly dissatisfying in that you need to know that parameter 0 is your gain and parameter 1 is your feedback, then you're right, and we'll come back to this. This is kind of the meat of the algorithm, I guess. The important things to note here is that previously our entire algorithm just looked like this bottom line, where we were multiplying the data in our audio buffer by a fixed gain. But now it's also composed of this multiplication and some operations of the dry sample mixed with the delay sample, where the delay sample is coming from this recursively attenuated buffer of all audio played through our algorithm. And then finally, we just iterate over our delay buffer by the number of samples that we've processed. So let's do that. I will take a shortcut. So I've just used kind of the checkpointing system and jumped to the 05, the contents of the 05 source directory. And you can see it's built. Open up our test host. Drag it in our plugin. Oh, what on earth is going on there? And you see we've got these extra parameters, and with a bit of luck, you see that we're able to modify these parameters in real time, and we actually have a plugin, if not very interesting, at least you can have a play with it. Maybe have some fun. So the final bit of this section is how we can tidy things up a bit. I mean, we have already touched on the fact that the parameter management leaves a bit to be desired, and we can tidy that up and also touch on serializing and deserializing your plugin state by using this object that is the audio processor value tree state. Again, like the previous section, this isn't particularly, it's less typing than the previous section, but this isn't particularly fun typing. It's stuff you need to know if you're going to create a plugin, but it's not particularly interesting or fun to change interactively. So the first problem with parameter management, the way we were previously doing it, is that there's this kind of unknown map, or at least you as the programmer need to know that your mix parameter is index 2 in the array of parameters you get back. You can probably handle this with 3 parameters, but there are plugins out in the wild that have tens of thousands of parameters. I mean, you can see why this scheme just isn't manageable in that case. So how do we use one of these? Well, we add a bit more state to our audio processor. We have an audio processor value tree state as a member variable, and we initialize it in the constructor. So the constructor looks mostly like it previously did. You can see we've got these 3 audio parameter floats, same IDs, same labels, same parameters. But rather than calling add parameter on our audio processor, we're passing this information to the constructor of the audio processor value tree state. This is the only other really interesting parameter. We're not using it here, but instead of a null pointer, you could pass a pointer to an undo manager, where the undo manager does what it sounds like. It will record all of the changes to any of your parameters and provide a mechanism where you can undo and redo those changes as you or your user wants. And this is a common piece of functionality in plugins. This is the mechanism where you can kind of hook into that. Now, rather than asking the audio processor class what parameters it's got and just getting a list, you can kind of index into this state using those private IDs that we had before. And now it's fairly easy to see how the parameters correspond to at least there's no more of having to know an index where you can use the actual ID to get the parameter that you want. The other thing that the audio processor value tree state does is makes it much easier to serialize and deserialize your plugin state. This might sound like nice to have rather than something that's fairly essential to all plugins, but when you're working with your plugin in your DAW, a user typically spends a while tweaking all the settings to get a sound that they really like. And when you hit save, your plugin needs to be able to save the state of your plugin so that when that session is reloaded, it knows how to configure itself to get back into exactly the same state as it was before that sounded nice. The 2 functions that do this on the audio processor class are get state information and set state information, both of which are called by the host when it wants to either save or retrieve your plugin state. And these both work on serializing to and deserializing from a block of memory managed by the host, not by you as a plugin author. The actual mechanics of doing this is fairly straightforward. When the host wants to save your plugin state, it will call get state information, and if you're using an audio processor value tree state, you can simply say state, create a copy of that state. In this case, we turn it into XML. If that is successful, we have pointed to some XML, and we just call this helper method called copy XML to binary, where it takes the XML and dumps it into this destination data, which is the memory, a block of memory provided by the host. You don't have to go via XML. You can trivially go straight from your audio processor value tree state to a binary representation. This will be much smaller and faster, but unless this process is really slowing you down, the benefits of having a human readable format for your save state easily outweighs. Well, when you come to debug and you can actually look at what a session was doing, you'll be very glad that you decided to keep it in XML or some other human readable form. And restoring your plugin state works in a very similar way, just the reverse process. So there's another helper function called get XML from binary, which you then have generate some XML, and then you can create a value tree from that XML and call state, replace state with this state that you've deserialized from this binary data. And we can do the same. We can build the plugin, load it in the test host. This time, if you tweak some parameters, right-click on the plugin name, click unload, and then when you reload, you'll see that all of those parameter values were where you left them. If you like to watch the world burn, you turned everything up to 1, then when you reload, you see that you're still in the same state. So please do that, load it up, have a play, and hopefully everyone will catch up